Welcome to this deep dive. Today we are exploring something truly fascinating. Artificial intelligence, tackling the incredibly complex world of competitive Pokemon battling.
That's right. We're diving into a new research paper that introduces an AI agent called PokéChamp, designed to play Pokemon at an expert level.
And our mission today is really to understand how it does this. What's unique about its approach? How does it leverage these powerful large language models, LLMs, not just for text, but for playing a strategic game? And maybe most importantly, how good is it really?
Yeah, we'll unpack its sort of novel integration of LLMs with a classic game theory technique called Minimax search. And as you see pretty quickly, competitive Pokemon is, well, it's far more strategic and challenging than it might seem. A genuinely tough testbed for AI.
Okay, let's jump right into that then.
Yeah.
Why is competitive Pokemon battling such a notoriously difficult problem for AI? I mean, on the surface, you're just picking one of four moves, right? How hard can it be?
Oh, if only. Competitive Pokemon is what we call a complex, partially observable game. First off, the scale is just immense.
How immense?
You've got over 1,000 Pokemon species, right? Each with unique stats, abilities, tons of possible moves, items, and now with terrestrialization, even different type combinations. The paper points out the theoretical state space, basically all possible game situations, is, well, it's mind-bogglingly large.
Right.
They estimate something like 10 to the power of 354 possibilities, just on the first turn.
Wait, hang on. 10 to the 354. That number is just, I can't even picture that. Why can't you just brute force it like a chess program might?
Because that number is just too big, way too big to explore exhaustively, even for the fastest supercomputers. And that's only part of the problem. It's the scale, yes, but beyond that, you've only got partial observability.
Meaning you don't see everything.
Exactly. You only see your opponent's active Pokemon. You don't know their whole team, their exact stats, their movesets, not initially anyway. You have to infer, make educated guesses, and update your beliefs as the battle goes on.
Right, like trying to figure out if that Snorlax has Curse or if their Dragapult is Choice Specs or Choice Scarf. You're constantly guessing.
Precisely. And games aren't short either. They can last many, many turns, so searching all the way to the end, just impossible within the time limits.
Ah, the time limits, right.
Yeah, on platforms like Pokemon Showdown, which is where they did this research, there are real-time constraints. A clock per turn and a clock for the whole match adds pressure.
So you can't just sit there calculating forever.
Nope. And then there's the metagame. It's constantly shifting. New strategies pop up. Certain Pokemon become popular. Mechanics like terrestrialization in Gen 9, they add huge strategic layers. Pokemon Showdown is key, though. It provides that stable environment for battling.
Okay, the challenge is clearly enormous. So tell us about PokéChamp. What's the big idea? How does it try and tackle this?
So PokéChamp is presented as this novel approach, right? It takes large language models, LLMs, and integrates them directly into the core workings of a traditional AI planning method, Minimax tree search.
Minimax. Okay. That's the one where you explore future moves, assuming your opponent plays optimally, trying to find your best move.
That's the core idea, yeah. But what's really interesting here is that PokéChamp tries to leverage the generalist capabilities of these big pre-trained LLMs.
So generalist, meaning?
Meaning models trained on just vast amounts of text and data. So they implicitly have some knowledge about strategy, logic, maybe even games just from that general training.
So are they training an LLM specifically on Pokemon battles? Feeding it thousands and thousands of games?
That's the crucial part, no. The paper really emphasizes this. The framework requires no additional LLM training on Pokemon data, zero fine-tuning. It uses the LLMs more like a black box consultant.
A consultant.
Yeah, querying them for insights within the Minimax search process. The goal is to find a strong, safe action against a smart opponent, blending that structured search with the LLM's general knowledge and inference skills.
Okay, this is where I get really curious. How do you actually use an LLM, which is basically about words and text, inside something structured like a Minimax game tree search? The paper mentioned three core ways, right?
Exactly. Standard Minimax builds this tree of possible moves and responses. But like we said, the Pokemon state space is way too big. You can't build the full tree. So PokéChamp uses LLMs in 3 specific places to make the search manageable and hopefully effective.
All right, let's break down number 1.
Okay, first is player action sampling. So instead of looking at every single legal move you could make, attacking, switching, whatever, which could be a lot,
Right.
the LLM gets prompted with the current game state. your team, what you see of the opponent, the battle history, your list of legal moves. And based on all that, it's asked to suggest just a small set of what it thinks are strategically good actions.
Ah, so the LLM acts like a smart filter,
Yeah.
pruning the tree right at the start.
Exactly. It dramatically cuts down the breadth of the search, makes it computationally feasible. Now, the system also includes a few other moves, like maybe the calculated best immediate move or a good switch option from another tool, just to be safe.
Okay, clever. Filter the options. What's the second pillar?
The second is opponent modeling. This is super important in a game where you can't see everything. You need to predict what your opponent is likely to do.
Right.
So here, the LLM is prompted again, but this time from the opponent's perspective. It tries to predict their most likely actions.
But wait, how can it predict the opponent's move if it doesn't know their full team or exact stats? Isn't that the whole problem?
Good question. That's where it gets quite clever. It combines the LLM's predictive power with external data. The researchers use that huge data set of past battles.
Millions of games.
Yeah, to estimate the hidden stuff, like typical stats, common abilities, likely movesets for a certain Pokemon at a certain skill level. This inferred probabilistic information is fed to the LLM along with what's visible in the battle. So the LLM uses this combined picture to make a better prediction of the opponent's likely moves. The paper even mentions how things like the damage calculation formula are sort of implicitly understood, helping the LLM predict outcomes.
So it's like, okay, given what I see and what I know about how, say, Garchomp usually plays, what's the opponent probably going to do? It's a neat way to handle the uncertainty. What's the third way it uses the LLM?
The third is value function estimation. Okay, so games are long, right? You can't search all the way to the win-loss screen. Minimax usually stops after a limited number of steps, let's say case steps into the future.
These are the leaf nodes of the search tree.
Exactly. At those points, you need a way to judge how good that game state is. Are you ahead? Behind? By how much? Even if the game isn't over.
You need a score for that position.
Right. And PokéChamp uses the LLM for this evaluation too. It gets prompted with the game state after those case steps. It considers things like, how many Pokemon are left on each side, their health, type matchup, speed control, win probability estimates, just a bunch of factors. And it uses its general understanding of strategy and game states to assign a value, a score to that position. This replaces needing a handcrafted, maybe fragile evaluation function.
Wow, that's a really sophisticated integration.
Yeah.
It's using the LLM for strategic filtering, for predicting opponent moves under uncertainty, and for evaluating complex board states, all without specific Pokemon training. That's pretty impressive.
It really is. It's a fascinating approach to leverage that broad knowledge from LLMs for very structured, complex decision-making.
So the big question then, how well did it actually work?
Yeah.
How strong is PokéChamp when you actually put it to the test?
They did a pretty comprehensive evaluation. First, they built that huge data set we mentioned. Over 3 million battles from Pokemon Showdown, including over 500,000 from high elo skilled players.
Right. And that wasn't just for testing. It helped with the opponent modeling too.
Exactly. It informed those probabilities. They noted stuff like higher elo games tending to be longer, suggesting deeper strategy.
Makes sense.
Then they did offline tests, like action prediction. They took past human battle situations and asked the LLM part, hey, what move do you think the human made here?
How well did it do? Better than random guessing.
Oh yeah, significantly better. Random baselines were super low, like 7% for predicting your own move, less than 1% for the opponent. The LLM got around 26-30% accuracy predicting the player's move, and maybe 13-16% for the opponent's move.
Still low, but much better.
Yeah.
Opponent prediction is harder, obviously.
Definitely harder because of the hidden information. But crucially, the accuracy went up a lot if you looked at the LLM's top, say, 3 or 5 predictions. It usually had the right idea in its top suggestions.
Okay, so it has some grasp of human strategy. What about actual battles? Did they test it in simplified scenarios first?
They did. They used small game puzzles. Things like 1v1 battles, which takes away the complexity of switching. In those head-to-head 1v1s, PokéChamp actually beat the previous best LLM bot, Pokémon, pretty handily. 86% win rate versus 76%.
Why the edge there?
They think part of it was PokéChamp's effective one-step look ahead, sort of calculating the immediate best outcome. And they also tested those complex mechanics like terrestrialization and Dynamax in specific puzzles.
Could it handle those? They add so much complexity.
Apparently, yes. The paper has figures showing it making smart switches based on Terra types or using Dynamax correctly to get a knockout, so it seems to integrate those rules into its planning.
Right, interesting. But the real test is full 6v6 games Gen 9 OU. against other bots and actual humans. How did it stack up there?
Okay, against other AI bots, PokéChamp with the big GPT-4o model was, well, state-of-the-art according to their tests. It crushed a strong rule-based bot called Abyssal, winning 84% of the time.
Wow.
And significantly, it beat Pokémon even when Pokémon also used GPT-4o. PokéChamp won 76% of those games.
Hold on. So even with the same powerful LLM, PokéChamp's framework, the way it combines the LLM and Minimax made the difference.
That's exactly what it suggests. And to hammer that point home, they tested PokéChamp with a much smaller open-source model, Llama 3.1.8b. And that version still beat Pokémon using the massive GPT-4o, winning 64% of the time. It really points to the strength of the integration method itself.
That's fascinating. Did they give ELO ratings based on these bot battles?
They did estimate them. PokéChamp with GPT-4o around 1268 ELO, the Llama 3.1 version around 1204, and Pokémon with GPT-4o lagging behind at 1020.
Okay, decent bot ratings. But the ultimate test, human players. On the live ladder, how did it do?
This is probably the headline result. They deployed PokéChamp onto the actual Pokémon Showdown ladder for Gen 9 OU, and it reached an ELO score above 1,300.
1,300 on the human ladder. That's
It is, but there's a caveat. The paper estimates its true ELO, if you ignore games it lost purely due to running out of time, would be somewhere between 1,300 and 1,500.
1,300 to 1,500 ELO. What does that translate to in terms of player skill? Where does that put it?
That range puts it firmly in the top 30%, maybe even the top 10% of human players on that ladder. That's expert-level play, no question.
Okay, but that timeout caveat sounds important. You said, ignore games lost due to running out of time. How many games are we talking about? Was that a rare occurrence?
No, it was actually pretty significant. The paper states that roughly 1/3 of PokéChamp's online games against humans were lost just because it timed out on a turn.
A third? Wow. So it ran out of time that often.
Yeah, the authors chalk it up to computational constraints. Basically, the complex Minimax search combined with the LLM queries took too long for the real-time turn limits in live battles.
So can you really claim expert level if it loses a third of its games because it's too slow? I mean, isn't managing the clock part of being an expert human player too?
That's a really fair point. It highlights a big gap between, let's say, strategic competence and practical performance under pressure. The 1,300-1,500 ELO estimates its potential, its thinking ability when it has time, but the timeout rate shows a major practical hurdle. Its brain might be expert level, but its reaction time, its computational speed, isn't always up to par for the live environment.
That definitely adds crucial context. Okay, so beyond the speed issue, were there specific strategies that PokéChamp struggled against when it did have time to think?
Yes, they identified two main culprits, stall tactics and opponents doing a lot of excessive switching.
Ah, stall. It's the bane of many players. Why does that give PokéChamp trouble? You'd think an AI could calculate its way through it.
Well, stall relies on defense, recovery, status, passive damage. It plays the long game, grinding you down over many turns. The paper suggests PokéChamp's limited look ahead, only searching stoss steps, and maybe its value function just don't capture those long-term dynamics well enough.
You can't see far enough ahead to realize it's being slowly worn down.
Kind of. Or it might misjudge the increasing uncertainty stall creates. They give an example where it might switch out unnecessarily or miss a key attack, like hitting a Blissey with Focus Blast, and then get sort of confused and make weird switches later because the game state is so muddled by the stall strategy.
Okay, struggles with the long game and managing uncertainty against stall. What about the excessive switching?
Right, so if an opponent keeps switching Pokemon frequently, it constantly changes the immediate situation PokéChamp is planning for. The authors think the AI's opponent model might not accurately gauge how likely a human is to switch repeatedly like that.
It expects more straightforward play.
Perhaps. And its limited look ahead makes it hard to predict and punish those switches effectively. The paper mentioned an example, I think it was using Focus Blast again. It might keep choosing that move because it's good against the Pokemon currently out, even if the opponent is clearly telegraphing a switch to something that resists fighting.
Yeah, I recall that. It sounds like you can get a bit stuck, a bit rigid against players who are really adaptive with their switches.
Exactly. And they even noted that human players who knew they were playing PokéChamp could potentially exploit that rigidity, which is why they stress testing anonymously.
Interesting. Did they try to address the speed issue with that PokéChamp Fast version? How did that go?
They did try a variant that dynamically chose between a quick look ahead or the full Minimax search, but it actually performed worse. Its estimated ELO was lower, maybe 1150, 1310.
Worse. Why?
The authors speculated a bit. Maybe the LLM's general knowledge it's training prior sometimes conflicted with the real-time situation in the fast-changing live metagame. Like, the LLM's static knowledge might have overridden more accurate, immediate calculations in some cases, leading to poorer decisions overall.
Wow, the static training data potentially clashing with the live, evolving meta.
Hmm.
That's a subtle challenge. So what were the main takeaways or future directions they pointed to?
Well, the obvious ones are improving opponent modeling, especially handling adaptation and that hidden information better. Also, finding ways to search deeper or wider without timing out a huge computational challenge, and making it more robust against players trying to exploit its patterns, like against stall or excessive switching.
And they had that point about testing on the ladder, right? An ethical consideration.
Yes, a strong recommendation, actually. They urged researchers to limit testing AI like this on the live human ladder, partly to avoid contaminating the huge pool of battle data that everyone uses for research, and partly just to avoid overwhelming human players with potentially super strong, tireless bots. They suggest AI versus AI competition is a better path forward for development.
Makes sense. Okay, let's try and wrap this up. What's the single biggest takeaway here? What's the core achievement of PokéChamp?
I think it's successfully reaching that expert level of strategic play in a really complex, partially observable game like Pokemon. And crucially, doing it by integrating these generalist LLMs with classic AI search without needing specific Pokemon training data. That hybrid approach is the key.
And connecting that to the broader world of AI, what does this signal about where LLMs might be useful beyond just, chatbots or image generation?
It really demonstrates a powerful pathway. Using LLMs for complex planning, for reasoning when you don't have all the facts, for modeling how others might behave in dynamic situations. It's taking that broad knowledge and pattern matching ability of LLMs and applying it to structured decision-making problems, which used to be purely the realm of more specialized AI.
So this blend, the LLM's broad understanding combined with the structured search of Minimax, it really makes you think. And for you listening, if this kind of hybrid AI can reach expert human levels in something as strategically deep and messy as competitive Pokemon with all its hidden information and dynamic play, what does that suggest about the potential for similar AI approaches in other complex real-world areas? Think about domains where we also face uncertainty, dynamic conditions, and the need to anticipate others' actions.
Yeah, it really poses the question, is the future of AI and complex decision-making less about one giant all-knowing model and more about cleverly integrating different strengths? The broad knowledge of LLMs with the structured rigor of algorithms. It's a really interesting direction.
Definitely a lot to chew on there. A fascinating look at AI tackling serious complexity in, well, a fun domain.
Indeed. Pokemon might seem like just a game, but as an AI challenge, it's incredibly rich.
Thank you for joining us for this deep dive.